Welcome to The Explainer. So today, we're literally cracking open the black box of artificial intelligence to look at the hidden mechanics of how AI actually translates languages. We are basing our entire journey today on a fascinating GitHub repository by a developer named Jeffrey Red. Specifically, we're looking at a project called mini-cross-attention. If you've ever found yourself wondering how complex neural networks bridge the gap between English and Spanish, or really any two distinct sets of data, you are absolutely in the right place. We're going to visualize exactly how the math makes it all happen.
Now, right off the bat, I want you to think about this core question. How does an AI actually know which words to look at when translating languages? I mean, when you paste a paragraph into a translation app, it doesn't just read word by word like a human with a dictionary, right? Grammar changes, word order flips entirely. Context is everything. The AI has to somehow figure out which specific part of the original sentence corresponds to the brand new word it's about to generate. So how does it physically do that? Well, the secret lies in a little something called cross-attention.
Okay, let's dive into this. Here is our roadmap for today. First, the encoder-decoder bridge. Second, self versus cross-attention. Third, the sequence reversal task. Fourth, visualizing the alignment matrix. And fifth, the foundation of translation.
Section 1. The encoder-decoder bridge. Connecting data islands.
To really wrap our heads around cross-attention, picture a literal bridge. It's a bridge connecting two completely separate data islands, the input data and the output data. To give you some quick context on why this repository is just so incredibly useful, it's actually part of a much larger series where the developer is building a mini large language model from absolute scratch. They started with word vectors in mini-embedding, built up through self-attention, created a mini-GPT, and even a chat interface. But we are stepping in right at step 6, mini-cross-attention. This is the absolutely crucial missing link required before the developer can move on to build a full English to Spanish translator. We're looking at the exact architectural piece that makes translation possible.
Section 2. Self versus cross-attention. The one new idea.
Now, if you've been following the AI space, you've probably heard a lot about attention mechanisms. It's everywhere. But the source material highlights one completely new idea that separates this specific project from everything that came before it. In every previous project in this developer series, the model used self-attention. That just means a single sequence of text simply looks at itself to understand context. It's kind of like an echo chamber. But cross-attention? That's a whole different ballgame. Cross-attention requires two separate sequences to function. It takes what we call queries from the target sequence, meaning what we are trying to generate, and matches them against the keys and values from the source sequence, meaning what we originally inputted. It's actively comparing two entirely different worlds.
This brings us to a highly important vocabulary word, the alignment matrix. The source tells us that the weight matrix produced by cross-attention is called the alignment matrix. It's described as the most interpretable output of any encoder-decoder model. And why is that? Because it literally shows you exactly which input tokens the model was staring right at, the moment it decided to generate a specific output token. It is basically a window straight into the machine's decision-making process.
Section 3. The sequence reversal task. A clever sandbox.
So you might be wondering, how do we actually prove this alignment matrix does its job without getting completely bogged down in messy, complicated language datasets? Well, the developer chose a brilliantly simple sandbox task to demonstrate this: sequence reversal. Instead of starting with, complex French or Spanish grammar, the model is trained simply to take a sequence of digits and spit them back out in reverse order. For example, you feed it 1, 2, 3, it spits out 3, 2, 1. It's a perfect test because the relationship between the input and the output is mathematically perfect and predictable. And that means the alignment matrix should be crystal clear.
And because this task is so razor-focused, the architecture is wonderfully lightweight. The configuration from the code is super accessible. The embedding dimension is set to just 32 because the task is so simple. It only uses 2 attention heads. They set it to run for 30 epochs, though the developer notes it usually converges, meaning it figures out the puzzle entirely, in just 20. And the whole thing only needs about 2,000 generated sequence pairs to learn the trick. There's no massive gigabyte-heavy data folder to download here. The data is all generated programmatically right on the spot.
Which leads us to this honestly mind-blowing fact. To train this entire cross-attention model from absolute scratch, it takes under 1 minute. Actually, let's emphasize that. It's under 1 minute on a standard CPU. No expensive graphics cards, no supercomputers required. It proves that you can understand the deep fundamental architecture of modern AI right on your everyday laptop if you just strip away the noise.
Section 4. Visualizing the alignment matrix. Reading the output.
Okay, now for the really fun part. Let's actually look at what that under 1 minute of training produces. And this brilliantly illustrates exactly what we want to see. According to the source, a well-trained model on a sequence reversal task produces a near-perfect anti-diagonal alignment line. Think about it for a second. If the model is outputting the last input digit first, its attention should logically start at the very end of the source sequence and systematically walk backward. That backward walk creates a diagonal line sloping in the exact opposite direction. It's like a giant puzzle coming together flawlessly.
Let's break down exactly how to read the visual plots generated in this repository. The plot is basically a grid. The shape of the grid is the target length multiplied by the source length. When you see a blue square pop up on this grid, it means the model heavily attended to that specific source position. So if you look at a specific row, let's call it row I, it's essentially the model telling you, hey, in order to generate my output token at this position, I looked right here at the source.
Now, what's really interesting about this is the physical shape of the matrices. The repository generates an image file to compare them side by side. The encoder self-attention creates a perfect square. And why is that? Because the input sequence is attending to itself, so the axes are exactly the same length. But the decoder cross-attention is rectangular. Because it's comparing two different things, the lengths of the input and output sequences can be entirely different. The developer notes that this visual shape makes the structural difference between the two mechanisms immediately obvious.
Section 5. The foundation of translation. Real-world application.
So we've reversed some digits, which is cool, but how does this actually apply to the real world? Well, the sequence reversal task is really just a proxy. The source material points out that this exact same alignment behavior appears in cutting-edge neural machine translation. If you were translating the English phrase the cat into the French phrase le chat, you would look at that alignment matrix grid and see the English word cat attending incredibly strongly to the French word chat. The anti-diagonal line we just saw with the numbers, that literally morphs into a dynamic, living map of grammar and vocabulary matching. Of course, this code doesn't just exist in a vacuum. The repository explicitly references the giants of AI research that this mini project is built upon. We're talking about the 2015 paper by Bodenow and colleagues, which actually introduced the whole concept of attention alignment for machine translation. Then there's Long's 2015 work on effective approaches to attention. And, obviously, the legendary 2017 Attention is All You Need paper by Vaswani and team, which cemented cross-attention inside the transformer architecture that powers pretty much all modern AI today.
By isolating cross-attention and proving it works with a simple number reversal, the bridge is officially built. The code is structured to map directly onto a larger architecture. So I want to leave you with a final thought directly from the developer's roadmap. Are you ready for Step 7, the full English to Spanish mini-translator? Because now that we truly understand the bridge, it's time to actually cross it. Thanks for joining me on this explainer. Keep learning, and I'll catch you next time.